Okay. You're sure? Don't mind. That's part of why we're here. But that's okay if there aren't any. We're going to move on today and look at what are called infinite geometric sequences. I think it's pretty obvious what I mean by an infinite geometric sequence. It's a sequence that's, series. It's a series that is infinite, which means we're continuing to add more and more and more and more numbers. And it's geometric. Pretty straightforward in terms of the language. There are, however, some real twists and turns to what we're dealing with today. I would say to you that in the end, this lesson is not that difficult, but there are some concepts embedded within it that are very slippery, intellectually slippery. You think you got your brain wrapped around them and they slip out of your grasp. One of them is the difference between what's called a convergent and divergent infinite geometric series. First of all, we only use the words convergent and divergent to describe infinite geometric series. Arithmetic series doesn't apply. Finite series never applies. It's all about infinity. And the thing that's greasy intellectual about infinity, of course, is for me anyway, I can't wrap my head around infinity. The fact that if you take infinity and you divide it by 1,000,000, you still have infinity. The fact that you can never get to infinity. So whatever concept you personally have of infinity in your head, it doesn't exist because you can always add more to it, right? So it's this very weird idea, infinity. And then we're going to be solving problems only with infinite geometric series if they are convergent. And in order to start understanding the difference between convergent and divergent, I've got two geometric series that we're going to explore in the warm-up. The first one, series 1, is 2 plus 1 plus a half. And we can make a note here, everybody, that in this first series, the first term is 2, and the common ratio is 1/2. Don't be sucked into thinking that the fact that there's 2's all over the place in these two series makes it important. I could have used other numbers than 2. On the other hand, in series 2, the first term also happens to be 2, but the common ratio is 2 instead of a half. And that, I don't think that really requires any explanation. You can see that this first series terms are being multiplied by a half or 0.5 regularly. And in the second series, they're being doubled, so r is 2. Any questions with that first part? I haven't really answered any questions that are in your handout yet, but does that make sense what T1 and R are equal to for those? Okay. So complete the following table. What is S1, S4? I mean, if I said to you, what is S1, and I don't have it in your handout, right? Your table starts at 4. But if I said, what is S1, you would say it's 2. S2 would be 3. S3 would be 3.5. Give a minute of thought as to where I'm getting these numbers from. Saying that S1 is 2, S2 is 3, S3 is 3.5. So hands up if you know. I'm not going to ask you. I'm just saying put your hand up if you know where I'm getting those numbers from. I really hope it's everybody. I'm adding up the terms, right? S1 means add up the first term. You get 2. S2 means add the first 2 terms. I get 3. To get the first 3 terms as a sum, I would add these 3 up. So we have, and just hold off on doing any real calculations yet. We have a number of options here. I suppose what we could do to find S4 is we could figure out the 4th term by multiplying the 3rd term by 1/4, and then we could add those all up, right? Let's do that. Let's add them up. And we're going to work in decimal here. I don't want to work in fractions. 3.75. And we could continue to do this, but I'm hesitant in doing that. I'm just wondering if there's a way that we can make our calculations more efficient, because we have to go up to 10. So first of all, I don't want to have to write out 10 terms, and I certainly don't want to have to add up 10 terms. Well, what we could do is use our formula for Sn, which says Sn is the first term. Now, you have a formula sheet that I've given you. I just want you to look at the formula sheet and make sure that my memory is right here. Is the first term times the common ratio to the n minus 1 over the common ratio minus 1. I want to know if I've written it down correctly. Because, man, Lord knows I'm not perfect. I make mistakes every day. But it's correct in this case, I think, isn't it? So if we customize this formula to include the first term of 2, the common ratio of 0.5, then we could load this into our table feature of our calculator and then just get the calculator to complete this. You catch my drift here? Why do the same calculation over and over again with different values of n when we can put this into our calculator and have it do multiple calculations in a split second, or as quickly as we can enter the numbers? So I have 2 multiplied by, in brackets, you could put a multiplication symbol there if you wish, 0.5 raised to the x. I don't need any brackets around the 0.5 because it's a positive number. Then minus 1. And remember what I said yesterday, it's not, in this formula, it's not raised to the n minus 1. It's raised to the n, and then it's minus 1. And this is over, well, 0.5 minus 1 is negative 0.5. I could put brackets 0.5 minus 1, but I'm just going to go divided by negative 0.5. And you know, what you could do, I'm not going to because it's not important, is you could take this 2 divided by this negative 0.5 and just put negative 4 out in front, because 2 divided by negative 0.5 is negative 4. You don't have to, though. So if I go to my table now, let's set up the table to start at 1 and go up by 1 automatically. If I go to my table, look at what it tells me S1 is. It tells me it's 2. S2 is 3. S3 is 3.5. Then it's 3.75, which is what we got. And then the other numbers are numbers we can just read off of that. I'm just going to pull it off so I can write on here. The next one's 3.875. Then 3.9375. Then 3.96875. If you go down to this, you're kidding. Check. And where was I? Oh, I know where I was. We had on the calculator, we had this 3.9688, and I started writing 3.96877 because I was about to explain to you that if you scroll over to your y and actually take a look at the number, it's not ending in 88. Your calculator is rounding it. Not that it's a big deal. I've got 3 more to go. The next one is at 8, which is 3.984375. 3.984375. And believe me, the point is not that they all end in 0.75. And the point is not what the actual numbers are. There's a bigger picture to what's going on here. Then this number which, you know what, I'm not even going to bother writing down all those decimals. It's not worth my time. The next one is 3.9922. This is obviously rounded, and with 10, it's 3.996 something. 9961, I guess, rounded. So, as well as not being the point that they end in 0.75, it is also not the point that you want to do this all the time. Okay, we're learning something from this. If we repeat the process for this one, then we can write Sn as the first term, which is 2, times the common ratio, which is 2, raised to the n minus 1 over 2 minus 1. Are you with me? Okay. So we enter that into y1 now, and we generate a new table. Of course, I don't really need to divide by anything because 2 minus 1 in the denominator is 1. So I go to my table, and let's just see if this makes sense. Is the sum of the first term 2? Yeah. What's the sum of the first two? 2 plus 4 is 6. That's right. 2 plus 4 plus 8 is 14. So we generate this list. Starting with 4, it's a sum of 30, then 62, then 126, then 254. Does that say 510? 510, 10, 22, 20, 46. 10, 22, 20, 46. Okay, so far, so what? Okay, you haven't really learned anything here. I'm just finding sums. The question now becomes really important and somewhat, as I've said, slippery or greasy. What happens to the sum of the terms in each of the two series as n approaches infinity? What does that mean? It means what's happening to the column y2 when we get to larger and larger values of n. Now, n approaching infinity is not just n being a large number. It's n being a really large number. So let's talk about the second series first, because we have it in our calculator right now. So as n approaches infinity, what happens to Sn? Well, it appears as though it just keeps getting bigger and bigger. And by the way, when you see something like 8.39E6, I think it's worthwhile explaining what that means. It means 8.39 multiplied by 10 to the 6. And I'm sure there's more decimals there other than the 8.39. We could certainly look. Yeah, it's that number. And as we continue to add more and more terms, this thing just keeps getting bigger and bigger. Look how big the number is now. It's in the billions or trillions. I don't know. It's a big number. And this brings up the common notion that you probably have. If you continue to add more and more stuff, doesn't it make sense that the pile's just going to keep getting bigger and bigger? I mean, it does to me. And I don't know quite how to convince you of this, but if you continue to do this, and if you have a few hours tonight, you can go home and continue to scroll. There's no limit to how big this number is going to get. It's just going to keep growing and growing and growing. So how do we answer this question? We say as n approaches infinity in series 2, Sn also approaches infinity. This is just a way of saying that the sum of the terms keeps getting larger. There's no boundary to how big it gets. It takes off forever. But let's take a look at series 1. Now I have to re-enter. I should have had 2 calculators on the go here, but well, I'll get a second calculator going now. And in this calculator so in this calculator I have the formula for Sn for series 2. In this calculator I'm going to put the formula for series 1, and I'm going by memory, but I believe it was 2 times 0.5 to the n minus 1, and then divided by negative 0.5. Am I right? So now I'm going to go to my table, and I'm going to scroll down. So I got to set my table up to start at 1 and go up by 1 on automatic. Okay, there we go. So 2, 3, 3.5, 3.75, 3. It's getting bigger, but it's getting bigger each time by a smaller amount than it was getting bigger by last time. Do you get that? That in and of itself is kind of tricky. It's getting bigger each time, but it's not getting bigger by a larger amount each time. It's getting bigger by a smaller amount each time. And strangely enough, I mean, it says 4 up here in the table, but when you look at the values, it's not 4. Now it says it's 4 there at 40, right? At n equals 40, it says it's 4. First of all, trust me, it's not 4. It's 3.99999999999. It's a whole bunch of 9s. And there's really no way for me to show that to you. I suppose I could fire up Microsoft Excel and tell it to show me an answer with 1,000 decimal places, but I don't think it's worth our time. Can you just trust me on that? Okay. So what's happening here, this is really difficult to visualize. I'll try showing this to you on a graph. What's happening here is when n is 1, there's a certain value of 2. And then when we add the next term, we get to, so this would be n equals to 3.5, and then we get to 3.75, and then we get to 3.8875, and then we get to, and what's happening is the value of the number is growing more and more, but it's never reaching, I gotta move this, it's never reaching 4. It keeps getting closer and closer to 4, but it never reaches 4. And I can explain to you, without using a calculator, why it can't reach 4. So let's imagine that I am 4 feet away from this wall. Okay, and we're going to ignore the length of my shoes and everything. I'm going to walk 2 feet towards the wall. That's probably about 4 feet here. I'm going to walk 2 feet towards the wall. And it shouldn't be lost on you that 2 feet, that's the first term. Right? What's the second term? Well, notice I have 2 feet left. The second term is half of 2. So if I add that half of 2, I add 1, and I'm at this position where I'm 1 foot away from the wall. The next term is half of the 1, which will take me to half a foot away. I'm always going to be adding half of the remaining distance to get to that 4. So no matter how close I get to 4, I will never get there. Which is a really strange thing. You can add an infinite number of numbers, but it never reaches 4. No matter how many numbers you add, you'll never get to 4. So what we would put here is as n approaches infinity, the sum of the terms approaches 4. And what we would say in mathematics, and this is really something that calculus hinges on. If you go on and take calculus next year with me, infinity is a concept that turns into real things. What this means is that at infinity, even though theoretically you can't get there, the sum will be 4. Or if I said, how many terms would you have to add to reach 4? You would answer infinity, even though you can't get to infinity. And maybe that's the whole point. It's an infinite number of terms. All right, let's take a look now at definitions. These two series illustrate two different types of sequences. Convergent is a series where the sum approaches an actual number as n. I better not use capital N here. I'll just do this. Convergent is a series in which the sum approaches a number as the number of terms you add approaches infinity. So series 1 was convergent. The word converge means to come together. So, for example, if you have cars driving on a 4-lane highway and that 4-lane highway turns into a 2-lane road, those cars converge. They come together. And if you take a look at this diagram I've shown you, you can see that the sum is converging. It's getting closer and closer to some number. So that's a way to remember it. Divergent is a series where the sum doesn't approach a number, it just explodes. It just gets bigger and bigger and bigger as the number of terms you're adding approaches infinity. And this would be an example that is illustrated best with series number 2. Now, this is not how we're going to do these problems. If you want to know if a series is convergent or not, you could do what we did in the warm-up, or you could do something else that we're leading up to. Okay? Any questions with those two terms or the first part of this lesson? All right. So, example, the first term of a geometric series is 3 and the common ratio is -1/5. Is it a convergent or divergent geometric infinite series? So the first term is 3. The common ratio is -1/5. Well, until I show you the secret, you can't do it any other way than putting your formula for the sum in for y1 and looking at what's happening to the sum. You know, looking at S1, S2, S3, S4, etc. So we're going to put in our sum formula here. Let's keep in mind -1/5 is the same as -0.2. It's just going to be easier for us to use that number in our calculator. So Sn is the first term times the common ratio, which is -0.2 raised to the n, then -1, over -0.2 minus 1. Now, a couple of things. This set of brackets is absolutely crucial. You cannot exclude that set of brackets. And because we're taking that thing raised to the n minus 1, we're taking that whole thing and dividing by whatever -0.2 minus 1 is, this set of brackets is also important. I think it would serve us well to figure out what this denominator is so we don't need a third set of brackets. All right, let's see what happens here. By the way, how many of you suspect you know the answer to this question, whether it's convergent or divergent? Okay, I won't ask you to confirm that, but just make a mental note of it and then we can check. So it's 3 brackets, another set of brackets, -0.5, no, -0.2, close brackets on the negative 0.2, raised to the x, then subtract 1 and close brackets on the entire numerator, or the part other than the 3, divided by negative 1.2. And before I go on, maybe we could just check something out here. The first term is 3. The second term will be 3 times negative 0.2, which I believe is negative 0.6. Am I right? Is 3 times negative 0.2 negative 0.6. Okay. The third term would be negative 0.6 times negative 0.2, which I believe is 0.12, but I would like some confirmation on that. We're not finding any sums yet. I'm just finding the terms. In other words, is 3 times negative 0.2 negative 0.6? You said the answer is yes. Is negative 0.6 times negative 0.2 positive 0.12? We talked about this, I think you and I talked about this, that the sum is going to go up and down because the common ratio is negative. When we add a negative term, that's going to drop the sum, and then we add a positive term, and it's going to increase the sum. So do me a favor and just ask yourself, what is 3 plus negative 0.6? That would be S2. It's 2.4, right? So if I've entered this correct, when I go to my table at n equals 2, I should get 2.4, the sum of the first two terms. Again, I'm going to start at 1 and go up by 1 automatically. Yep, it's working. So let's see what happens here. It goes from 3 to 2.4, and then 2.52, and 2.496, and 2.5008, and 2.4999, 2.500032, 2.4999936. Those of you that had a suspicion about whether it was convergent or not, were you right, do you think? Turns out it's convergent. It's converging on 2.5. This is interesting. I'm interested by stuff like this. This is what one of the convergent series looked like in the warm-up. This was convergent. I'm going to draw what the convergent one looks like in the example we're working on right now. I'm going to exaggerate it, though, because I can't draw the difference between 2.50002 and 2.4999 something. Excuse me. This is 2.5. And in fact, with this one, I'm not even going to put dots. I'm just going to put a curve. That's what the sum graph looks like for that one. For this one, it looks like the following. Goes up above it, and then it goes below it. And then it goes up above it, and it goes below it. But each time it goes up or below, it goes up or below less than it was going up or below before. This thing is wobbling up and down, zeroing in on, converging in on 2.5. So, does the series converge or diverge? It converges, which means we could call it a convergent series. If it's convergent, what is the sum? So now we start to introduce an actual sum. If I say to you, 3, well, I've got it written here, so I don't need to write it again. If I say to you, plus ... what does that equal? Then I'm asking you to add an infinite number of terms. And since as n gets bigger, the sum approaches 2.5, the sum of the infinite series is 2.5. And I know you can never get there, but we still say the sum of the infinite number of terms is 2.5 if you could get there. Any questions with 3? Or, sorry, 1? Any questions with 1? Okay. If a series is convergent, so this is a special formula. I want you to notice there's no n in this formula. We could write S infinity if you wanted to, but it only works if the series is convergent. So, in our warm-up, do you all agree that this was a convergent series? What was the sum approaching? Do you remember? This is the warm-up one. It was 4, wasn't it? It was 2 plus half of 2. You're always approaching 4. So this equals 4. It's convergent, which means we could use this formula. The first term over 1 minus the common ratio. Figure out what 2 over 1 minus 0.5 is. It's 4, isn't it? Well, that's the sum. In the one we just did, I need some help here. Was it 3 plus negative 0.6? Yes. This one had a first term of 3 and a common ratio of negative 0.1. So if we use this formula, S would be the first term over 1 minus negative 0.1. No, it wasn't 0.1. It was 0.2, wasn't it? It was 0.2. My mistake. This is a 2. Go ahead and figure out what you get. You're going to have to go 1 minus negative 0.2 first, and then take 3 divided by that. I think you get 2.5, don't you? I want to do one last thing before we learn one final thing and finish off this lesson. If I go back and look at this series here, okay, and I say to you, what's the sum of the infinite number of terms? And you go, well, geez, there's this formula on my formula sheet. I'm going to use it. What will we get? Let's see. 2 over 1 minus the common ratio is 2. We get 2 over negative 1, we get negative 2. Can that possibly be what the sum of these numbers is going to give you? No, because you're not allowed to use this formula for this series because it's not convergent. You can't use it all the time. You can only use it if it's convergent. All right. Ouch. Further examples. Decide whether each infinite geometric series is convergent or divergent. So the first term here is 10. The common ratio is what we multiply 10 by to get 2, which is a fifth. But can we use, and can you confirm that when you take 2 times a fifth, you get 2/5? You do. Can we use this formula? Well, we can if it's convergent. Do you think it's convergent? How do you know? Those of you that are saying, I know it's convergent, and you're right, it's convergent. How do you know? Jack?
Each subsequent term is smaller, which means that it can't possibly pass a certain number.
Beautiful. Each subsequent term, each next term is smaller than the one before. How do you know it's smaller other than looking at these numbers? Well, the common ratio is less than 1. And in fact, I'll tell you right now that if the common ratio is less than 1, it will be convergent. By less than 1, I mean between 0 and 1. Okay? And we can go even further and take a look at example 1. The common ratio was negative 1/5. And I will tell you right now that if the common ratio, we will formalize this in a second, if the common ratio is between negative 1 and 1, but not equal to 0, obviously, if the common ratio is any number between 0 and 1, or between 0 and negative 1, it's convergent. And the reason is those numbers create subsequent terms, next terms, that are smaller than the one you're adding to. So it doesn't take off forever. So in case you haven't picked up on it, our days of doing this are over. That's not what you do anymore. So this is convergent, which means the sum will be equal to 10 over 1 minus 1/5. However you want to figure that out, do so for me, please. I'm going to want to say 12.5. When you work out the bottom, you get 0.8. And when you take 10 divided by 0.8, you get 12.5. There's no sum here. This is not convergent. This is divergent. And all you need to do is look at the common ratio. The common ratio is 3. It's outside of that domain of numbers from negative 1 to 1. And I have some things to add here. So let me walk through this with you. The rule for deciding whether the geometric series is convergent or divergent is simple. In your notes, it says the common ratio lies between negative 1 and 1. If that's the case, then it's convergent and it has a sum. Really, I should say it lies between negative 1 and 1 and is not equal to 0. And I've changed my note package for next time. You cannot have a common ratio of 0. Well, I guess you could, but all the terms would turn into zeros at some point. And so when I say to you in the box there, convergent is negative 1 is less than r, which is less than 1, you should also know that r cannot equal 0. That slipped my brain when I typed up my notes. So, in the past I've just taught that right from the beginning. Can we find the sum of this infinite series? Yeah, because look at the common ratio. Negative 1/3 is between negative 1 and 1. Here's that number line again. Negative 1, the common ratio can't be negative 1. The common ratio can't be 0. The common ratio can't be 1 for convergent, but it can be any other number in between those values. So since r equals negative 1/3 is here, we can go ahead and use this fancy formula, t1 over 1 minus r. And we'll take t1, which is 5, over 1 minus negative 1/3. Give you a little calculator minute here for you and your calculator to get to know each other better and make sure you can get the right answer. I'm going to say 3, but no. 3.75. So this works out to 3.75. I would say to you at this point in the lesson, just make sure you can get 3.75. If you cannot, just make a note of it. And when I ask you later on when I do my rounds, how did it go today? Just make sure you ask about that so that you can figure out how to use your calculator effectively. What's the sum of this infinite series? The answer is infinity. By the way, could you have an infinite series that has a sum of negative infinity? Yeah. When we say it's divergent, it could be approaching infinity or negative infinity. But since r equals 3/2 is here, outside of that domain of acceptable values for convergence, this sum doesn't exist. Or you could say s equals infinity. I mean, you could say that, right? But as a number, infinity isn't a number. It's a really mind-blowing kind of thing. You're adding an infinite number of things to get a finite answer. Any questions with that final example? All right. So some practice problems, page 63, 1, 2, and then 5 through 10. We are done the units, so tomorrow when you come in, I will have some review problems that you can work on, and we will go through a review together of all of the topics. Thursday, I like 2 days for review because if I give you the review materials tomorrow, you're going to have questions about them. We can go over that Thursday. Exams Friday. Don't forget that assignment is due tomorrow. You know what? I'll tell you what. If you give me the assignment Thursday, that's okay. I'll take it in Thursday. But you will not get it back before you write your exam. Right? So I'm giving you an extra day if you feel you need it. If you hand it in tomorrow, then after I get everybody else's in on Thursday, I will hand it back to you Thursday so you can see it before you write your exam. It's up to you. Okay? Get to work. I'll come around in a couple minutes and help you out.